So, what exactly is a radical? In simple terms, finding a radical is the opposite of raising a number to a power. If multiplying is the opposite of dividing, then finding a root is the opposite of finding a power. Let's quickly break down its parts. When you see this notation, the nth root of a, you're looking at three key pieces. The checkmark symbol itself is the radical symbol. The small number n tucked into the corner is the index. This is very important. It tells us which root to find. If you don't see an index, it's always a square root, meaning the index is 2. And the number a inside the symbol is the radicand. Now for the most important rule that connects everything. The expression, the nth root of a equals b, is the exact same thing as saying b raised to the power of n equals a. Simply put, the answer to a radical, when raised back to the power of the index, gets you right back to the number you started with inside. Let's see this in action with the most common radical, the square root, where the index is 2. The square root of 25 is 5. Why? Because 5 squared equals 25. A key rule for square roots is that the number inside, the radicand, cannot be negative. So the square root of -9 is not a real number. Next up is the cube root, where the index is 3. The cube root of 8 is 2. This is because 2 cubed, or 2 to the third power, equals 8. But here's a crucial difference. With a cube root, the number inside can be negative. The cube root of -27 is -3, because -3 cubed gives you -27. This brings us to a simple, powerful pattern for all other roots. It all comes down to whether the index is even or odd. If the index is even, like 4, 6, 8, etc., it behaves just like a square root. The number inside must be non-negative, and the answer will be non-negative. For example, the fourth root of 16 is 2. If the index is odd, like 5, 7, 9, etc., it behaves just like a cube root. The number inside can be any real number, positive or negative, and the answer will have the same sign. For instance, the fifth root of -32 is -2.
These properties are the essential tools you'll need to simplify and solve complex expressions. Let's get started with our first property. First up is the product property. This rule says that if you're taking the root of two numbers multiplied together, you can split them into two separate roots. Look at the formula. The nth root of a times b is the same as the nth root of a times the nth root of b. This is incredibly useful for simplifying. For example, to find the square root of 72, we can rewrite 72 as 36 times 2. The property lets us split that into the square root of 36 times the square root of 2. Since the square root of 36 is 6, our final simplified answer is 6 square root 2. Next, we have the quotient property, which is just like the product property, but for division. It states that the root of a fraction is the same as the root of the numerator divided by the root of the denominator. Let's look at the first example, the fourth root of 16 over 81. We can split this into the fourth root of 16 on top and the fourth root of 81 on the bottom. The fourth root of 16 is 2, and the fourth root of 81 is 3. So our answer is simply 2/3. Now for a cool one, the root of a root property. If you ever see a root inside of another root, you can combine them into a single root by multiplying their indices. The index is that small number that tells you what kind of root it is. For example, the square root of the cube root of 729 looks complicated, but we just multiply the indices. That's a 2 for the square root and a 3 for the cube root. 2 times 3 is 6. So we're really just finding the sixth root of 729, which is 3. All right, these next two rules look similar, but they have one crucial difference. It all depends on whether the index, n, is odd or even. First, when the index n is odd, the root and the power cancel each other out perfectly. The cube root of -5 cubed is simply -5. The sign stays exactly the same. However, when the index n is even, there's a catch. The result of an even root can't be negative. To guarantee this, we must take the absolute value. For instance, the fourth root of -3 to the fourth power, the root and the power cancel, but because the index 4 is even, our answer is the absolute value of -3, which is +3. This is a vital rule, especially in algebra, where x in the expression square root of x squared could be a negative number. The correct simplification is always the absolute value of x. Finally, let's cover the most important warning, a very common mistake. Radicals cannot be distributed over addition or subtraction. Let's prove this with a simple example. What is the square root of 9 plus 16? First, you have to do the addition inside the radical. 9 plus 16 is 25. The square root of 25 is 5. Now, what if we tried to do it the wrong way? The square root of 9 is 3, and the square root of 16 is 4. If we add them, we get 3 plus 4, which is 7. Clearly, 5 is not equal to 7. So remember, always perform the operation inside the radical first.
Now, we're going to demystify a concept that connects two areas of math you might think are separate: exponents and roots. We're talking about rational exponents. What if I told you that a square root or cube root is just another way of writing an exponent? That's exactly what a rational or fractional exponent is. This is a powerful idea because it allows us to use all the standard exponent rules we already know to simplify expressions that involve roots. Let's break it down with this table. First, the single most important concept to remember is the basic rule. When you see a base, let's call it a, raised to a fractional power, like m over n, just remember the phrase power over root. The numerator, m, the top number, is the power. The denominator, n, the bottom number, is the root. Look at the example. 8 to the power of 2/3. Following our rule, the power is 2, so squared, and the root is 3, so the cubed root. This means you're taking the cubed root of 8 squared. Now, let's look at the simplest case, a unit fractional exponent. This is just a fancy way of saying the power on top is 1. For example, 64 to the 1/3 power. Here, the power is 1, so we don't need to do anything with it. The root is 3, so 64 to the 1/3 power is simply the cube root of 64, which is 4. A 1/2 power is a square root, a 1/4 power is a fourth root, and so on. Okay, so what if the power isn't 1? We actually have two ways to solve it, and they both give the same answer. Let's use the example 16 to the 3/4 power. The first method, which I highly recommend, is to do the root first. This keeps the numbers small and easy to work with. First, take the fourth root of 16. What number multiplied by itself 4 times equals 16? That's 2. Now apply the power, which is 3. Take that result, 2, and raise it to the third power. 2 cubed is 8. The second method is to do the power first. First, you'd calculate 16 to the third power, which is 4,096, a pretty big number. Then you'd find the fourth root of 4,096, which of course is also 8. As you can see, both paths lead to the same answer, but dealing with the root first is almost always easier. What about negative fractional exponents? The rule is exactly the same as it is for any other exponent. A negative sign simply means take the reciprocal, or flip it. If we have 32 to the -2/5 power, the first thing we do is handle that negative sign. We flip it to the denominator, making it 1 over 32 to the +2/5.
From there, we just solve the denominator. Take the fifth root of 32, which is 2, then apply the power, squaring it, which gives us 4. So our final answer is 1 over 4. Finally, here's the best part. The whole reason this is so useful is that all the standard exponent properties you already know still apply. When you multiply terms with the same base, you add the fractional exponents. When you divide, you subtract the exponents. When you raise a power to another power, you multiply them. And you can distribute a fractional exponent to each factor in parentheses. Being able to convert roots into exponents lets you use these simple, powerful rules to solve much more complex problems.